Hello, everybody. Thank you for attending. My name is Mark Lockbeeler. I'm with Hortonworks. This is my 5th year in the Hortonworks Partner Engineering team. I'm joined by a colleague at HPE, Vipla, who is a Spark developer. Let you introduce yourself. You want to?
Yeah, my name is Vipla. So as you said, I work in HPE Enterprise Solutions and Performance Group, developing reference architectures for big data workloads like Spark and Hadoop, and evaluating emerging technologies.
Okay, thanks. Thank you, Vipla. So our agenda today, we're uncovering a Spark 2 benchmark that we did together in a Houston lab. The agenda, I'll cover quickly what's new with Spark 2. I'll go over the architecture, talk a little bit about Spark on Yarn and why we love it so much here at Hortonworks, and what's new. Then we'll get into the meat of this presentation. Vipla will go through the benchmark with the bullets that you see up here, culminating with the results of the benchmark. And then we'll do Q&A. So with that, I'll jump right into it. So those that aren't familiar, I don't know who could not be familiar with Spark, but for those that aren't familiar, everything's based around RDD, data frame data sets, in memory, distributed compute processing. So with Spark, you get the opportunity to run your favorite SQL. There are SQL libraries. You've got streaming capability. You've got machine learning, artificial intelligence. You've got the opportunity to do graphing with GraphX. And there's batch capability. So all of those services are built on Spark Core. You can use your favorite language for those that aren't familiar, whether that's R, SQL, Python, Scala, et cetera, Java. And then, of course, Spark can run in a standalone cluster as a Spark-only cluster. It can run with Apache Mesos as an orchestrator. And we love it to run on Yarn. So there's 3 different ways you can execute with an orchestrator. Now, Spark with Yarn, everybody's familiar that we do have the concept of labels, and those labels allow us to do soft partitioning and support scheduling of jobs to nodes like that may have GPU. And so with Spark on Yarn, we're able to use queue placement policies, and we're able to run on a Kerberized secure cluster. There's 2 modes to running Spark on Yarn. One is that the Spark driver sits on a client outside the cluster, and that's really good for your dev environment. But then when you have matured your process, your Spark job, you can run it in cluster, and so the client just submits, and the Spark context lives in the app master. So that's really good for production running. Now, obviously, we believe running on Yarn is the best way to run Spark, and you know, who wants to bring all their data out to the edge? That just doesn't make a lot of sense. So distributed compute in Yarn, we believe Hadoop's the best place to run it for big data. Now, with Spark 2 over Spark 1, there were API improvements, SQL 2003 support. There were plenty of performance improvements. Structured streaming was updated. There's an RUDF that's now supported, and operational improvements. And I'll hit highlights on all of those so we can get to the bench. So the new and updated APIs, there's a unified data frame and dataset API, and it provides type safety for data frames. And there's a new Spark session API, which replaces the SQL context and Hive context for data frames and dataset APIs. There's a new streamlined configuration API, and there's an improved aggregator API. Now, as far as SQL improvements, there's now full support for 2003 SQL. There is a native SQL parser now available. There's native DDL capability. There's subquery support. There's native CSV support, data source support. There's off-heap memory management now that's available, and Hive-style bucketing. With performance, there's a new concept called whole stage code generation. And that's going to give you about 2 to 10 times performance improvement on common operations for SQL and data frames. And some other improvements around Parquet scan throughput, improved ORC performance, and there's many improvements in the Catalyst query optimizer. And there's also improved windowing functionality. With the ML Lib, we've got the new data frames-based API, and there's also a number of new features in the machine learning API. I'm not going to go through them all. You can see them up here, but there's a heck of a lot of improvement there. Streaming SQL, we now have a new API called structured streaming, and it runs on top of SparkSQL and the Catalyst optimizer. And the structured streaming is using the same data frame dataset API as it would with static data sources. So that's an efficiency improvement. Now here at Hortonworks, we recently launched 2.6.5, and obviously we just launched 3.0, and they have Apache Spark 2.3, and in the highlights there are the ORC Parquet feature parity. We also have, for Pandas users, we have a Python UDF. And now within the structured streaming, we support stream joins. And also with structured streaming, we've got millisecond latency in some of the alpha releases there. So with that quick introduction to the Spark 2, I want to turn it over to Viplava, and he will talk through the joint benchmark that we did together.
Thanks, Mark, for the nice introduction to Spark 2.0. Oh, sorry, I should go on.
No problem.
Okay, so just quick background on why we did this evaluation of SparkSQL with Spark 2 versus Spark 1. Essentially, my group in HP works on reference architectures for big data solutions, as I said, for Spark and Hadoop. I'm not sure how many of you have seen a reference architecture document, but essentially they are like complete, verified, and optimized cluster configuration so that the customers can get started with their deploying their workloads as quickly as possible. So if you should see one, actually, I think there are links at the end of the session. So the documents, essentially the reference architecture document includes like all the configuration tuning information and the best practices and the deployment information and like including the bill of materials, so that if you want to get a Spark cluster up and running quickly, you have all the information there. So, but for that, as I said, we need to tune that cluster. We need to provide the cluster tuning information, right? So for that, we need to pick ideally a customer workload, but we don't have customer workloads. So we pick a benchmark, a representative benchmark for picking the Spark workload. In this case, essentially we chose, for Hadoop, it's probably everybody knows it's Terasort. But for Spark, we pick a Hive test bench, which is essentially TPC-DS benchmark, standard for SQL. But you cannot say it's TPC-DS benchmark because you need to follow strict guidelines to say it's TPC-DS benchmark. So it's Hive test bench, which is similar to TPC-DS benchmark. Quickly, it says 2.x. Just quick note. Initially, we worked with 2.1 first. We did extensive testing. That was with HTTP 2.6.1. And then when we did it with 2.2 with HTTP 2.6.3. And as Mark said, there is a 2.6.5 now with 2.3, Spark 2.3, but we haven't tested that. Just so 2.x is 2.1 and 2.2 both. And typically 2.2 is a stability release, so it's not much improvement. It's more or less similar figure. Okay, with that background. Okay, so in general, why do we, again, some more information on why cluster tuning is important. Probably you would have realized by now, like Spark and Hadoop, the default configurations out of the box typically are good for trying out on your laptop or a sandbox VM, and definitely not optimal for your enterprise workloads. So, and then on top of that, you have like large number of hundreds of configuration parameters to tune. Those are the documented ones. And then there are thousands of undocumented settings you can tune. And then, the tuning cluster will benefit all the applications instead of individually tuning. Again, I have a lot of configuration tuning information, so I might be going through some of the slides quickly, but the information is there on the slides for your reference later, okay? Just quickly, Spark performance tuning, essentially these are all the factors that go into performance improvements like hardware, CPU, memory, storage. I'll go a little bit detail in each of them. Sorry, I went up. So these are general hardware guidelines. These are essentially from Apache Spark website, so I'm going to go through quickly. Essentially, Spark benefits from, give more hardware, it's very happy, more CPU cores, more memory, flash storage for intermediate storage, and faster network fabric is all good. Spark really scales well to, hundreds of tens of CPUs, of course, per node, because it does not, it uses threads for tasks, not like process for tasks like MapReduce. Okay, typically they suggest 8 to 16 cores, and we choose 16 cores machine nodes for our reference architecture. Again, obviously, Spark is known for in-memory processing. It started, became popular for that, so it can make use of hundreds of gigabytes of memory. We suggest at least 512 typically, and maybe more. Again, network. Typically, network is not a big issue, but it really plays a role when you are doing shuffles, because you're pulling a lot of data, you're shuffling a lot of data. So 10 gigabit is recommended, and nowadays kind of standard. Local disk, again, as I mentioned, like typically Spark uses local disk for intermediate storage, so that all the disk spills when all the RDDs, when you're serializing, or it doesn't fit in memory. And then also for the intermediate, the map output files for the shuffles. So typically SSDs are better. So again, that was quick hardware tuning, you can say. And then before going into the software components, I just wanted to give a picture of where everything fits. So obviously on the left, you have the Spark client, which is submitting applications. So that's your Yarn client from Yarn point of view. And it submits jobs, Spark jobs, and in the Yarn, essentially it talks to Yarn resource manager, which is the brain controlling everything. And then which first starts a Spark application, Yarn application manager, which is a Spark application manager in this case. And then you have node manager, essentially spawning multiple Spark executors. And within executor, there are multiple tasks, one per core. Okay, so the Spark driver, as Mark said, it either sits in the Spark client, or in this cluster mode, it sits in the Spark, the Yarn application manager. So that is the whole setup. As I said, and there is a HDFS for the storage layer on, typically in Hadoop, right? So for HDFS, again, it's better to tune HDFS because when Spark is reading from HDFS, essentially your RDD partition size is kind of decided by Hadoop input format size, where essentially it depends on the split size. And Hadoop, essentially your Spark RDD size is same as the Hadoop, the HDFS block size. So again, the default is 128 megabytes, but typically for large workloads, you might want to bump it up to 256 or 512. That's what we do typically in our reference architecture. And then the next one is this DFS name node handler count. That's essentially the default is 10, which is really not good for enterprise. Big when you're dealing with big data, you might want to bump it up to 100. Again, you might have, whenever you're dealing with large data sets, you'll have all kinds of timeout exceptions. Sometimes the error messages are really not so obvious. It says, you can see one example here, java.io.io exception, unable to close file because the last block does not have enough memory number of replicas. I don't know what are you supposed to do with it. But essentially, it's a timeout issue, and you just set this retries to 30, which is, the default is 3 or 4, which is not enough. Your error messages will go away. Some more Yarn tuning, essentially, because Spark is working with Yarn here, so you need to set both of the configuration in tandem, like you need to tune them together. For example, Spark executor, when you say Spark executor memory is so much and cores are so many per job, so it essentially results in resource request to Yarn resource manager. And that means essentially they have to be compatible, Spark requests should be compatible with the yarn limits. There are a couple of settings I mentioned. In general, the total number of the cores and the total amount of memory per node that's available. This is the yarn settings for those things. Obviously, Spark cannot exceed beyond that. So that's you need to make sure that it's enough. Some more, and this is the top one. I'm not going to go through detail, but essentially it tells you how you can figure out the number of containers. But do remember that one container is kind of needed for yarn application master. So your total executors will be one less than the total number of containers available. In general, there are other settings like you can have minimum and maximum memory and cores per container. In yarn settings, I didn't list here, but all those things essentially you need to tune such that you maximize the utilization of the memory and vCores. Okay, so that was the yarn tuning. Now coming to the real Spark tuning itself. So as I said, a MapReduce spawns a process for each task, whereas Spark essentially uses threads. So it's really efficient. You can say that essentially it's free to start a task on Spark. So, but at the same time, it also introduces a new parameter to tune because it's not automatic. We need to specify how many cores per executor Spark needs to use. So that means again it has to work within the boundaries of yarn. So the setting probably is Spark executor cores, and the default is 1, which is definitely not good. Okay, so what is the problem with 1? So typically like if you have 1 executor core per executor, that means essentially you want to maximize the memory utilization. You will divide the total memory into the number of executors. So you'll essentially you'll have a bunch of executors, many executors, and each executor will be having only a little bit of memory. And if you are dealing with, let's say, big data sets, like then your partition size might not fit into the executor memory, and then you might run into spilling to disk and sometimes out of memory errors. So again, the another problem with that is like essentially you might be knowing that to avoid shuffles, you have in Spark there's something called broadcast variables. So in that case, these things have to be sent one per each executor once. And if you have too many executors, you need to send multiple times and more network throughput and more memory because it's all the executors. And again, there is each executor also has some memory overhead on top of Spark memory. That and the minimum is 384 MB, or it's 10% actually, minimum of 384 or 10% of executor memory. So if you have a very small executor, you're wasting a lot of memory. For example, if you have 1 GB executor, so your 40% is overhead. What about on the other hand, if you give too many cores per executor? So that also has issues because that means you will have, essentially you're dividing the total memory into fewer number of executors. So you'll have larger heaps per executor. So that means you will have larger GC pauses because you're collecting a lot more garbage, before the GC kicks in. And it's also having too many concurrent threads going, in one per executor also is known to have poor HDFS throughput, so you don't want to have too many. Typically, the recommendation is 5, but as we'll see, later in the results we found, it's around 9 for this particular configuration we used. So you might want to experiment and then figure out what is the real, optimal number. For the memory, obviously, it depends on your application, how much memory your application needs sometimes. But typically, the way to divide it, first how to decide how much memory you want to give is, first you figure out the cores per executor, which gives you essentially the total number of executors, and to maximize your memory, essentially you divide that by your total number of executors. That gives you how much executor per memory you want to give. You might want to tune up and down depending on your application. With very large heaps, again, as I said, you might run into GC issues. For the Spark driver, typically, your processing has to be done on executors, not in the driver, so you don't want to collect too much data into the driver. Otherwise, you'll run into this out-of-memory errors. If you do run, there is a setting to increase the the driver memory, which sometimes I had to increase. There is another setting which is useful, but for that you need to understand a little bit of memory model of Spark. As I said, there's an executor memory overhead on the bottom, which is a minimum of 384 or 10% of the executor memory, and the remaining memory is essentially divided it into two broad categories, like Spark execution memory and Spark storage memory. Execution memory is used for shuffle output, like intermediate buffers and all that, and Spark storage memory is where your hard DD cache and all those that type lives. Okay, so there is a setting. So just in prior to Spark 1.6, these two were fixed based on the settings mentioned in the middle bullet. But essentially that means if you run out of one of those, you're tough luck. You will get out of memory or spills essentially mostly. But with Spark 1.6, they introduced a new model called Unified Memory Manager model, in which case it's more flexible. So in this case, essentially there is no static division. Let's say if you run out of execution memory, it can make use of storage memory if storage memory is not being used. Same way, vice versa also, it's true. But sometimes you might want to reserve something for your RDD caches. So for that, there is a provision that Spark memory storage fraction, which is, you can say that I need more memory for my RDD, so that execution memory get into the storage memory. Okay, the default is 0.5. That means half-half. But typically it gives you good out of the box, but sometimes you might want to tune it. And this is probably the number one performance issue, cause of the performance issue, the Spark shuffle partitions. Basically, Spark shuffles are involved whenever there are wide transformations going on, like whenever there are group by keys or reduce by keys or any aggregations in general. And basically there is the reduce side partition number is default is 200, which is most likely not good, particularly when you have a large cluster and when you're dealing with large data sets. Because in our, as you'll see in our reference architecture, we have about 450 or something like 540 cores. So that means you're not really utilizing all the cores. It will use only 200 cores. And also there is a limit about shuffle block of 2 GB. You might run into overflows and all that stuff. But typically, the recommendation is to use at least the number of the executor cores, or a multiple of it, because you want to use all of the cores. Also, for in general, hashing schemes prefer prime numbers, so you might want to put a number prime numbers closer to the number of cores. Okay, the compression can improve performance too. Basically, it results in less disk I/O and network I/O. Typically, compression and decompression will burn some CPU cycles, but the benefits outweigh the whatever CPU overhead you have when there is a large amount of data. In general, obviously, compression results in less storage. This is the setting: compression, I/O compression codec. Excuse me. And there are 3 codecs provided out of the box: LZ4, LZF, and Snappy. In general, and the default is LZF4, which is good in general. You don't have to really change, but you might try out and see. These are the places where Spark uses compression for compressing map output files during shuffle, for compressing data spill during shuffles, for compressing broadcast variables, and compressing serialized RDD partitions. The default for the first 3 is true, but for compressing serialized, it's false. Again, by compressing, you might save some memory by enabling that. Next is the serialization type. It also plays an important role. Probably you might have heard about it. By using serialization, it can improve the memory usage. By default, it uses Java serializer, which is known to be slow, and there is a Creo serializer, which is typically more efficient and compact. You set it using that setting. And then in general, SparkSQL automatically tries to use, whenever that data frames are involved, tries to use automatically, so you don't have to tune. But if you're using RDDs, you might have to, you should use Creo's serializer. And there are a couple of other last settings. So one is the filter push down. When you're when you're storing data in ORC or Parquet formats, SparkSQL can push the filter down into either ORC or Parquet. Just please remember that, note that for Parquet, the filter push down setting is true and it's enabled, but for ORC, the filter push down is not enabled. So you definitely want to enable. I'm not sure why they put it false. And then again, generally, this is a good tip for large. Whenever you are doing large data sets, I said there will be a lot of network timeouts and a lot of executors dying, and you will see executor lost and weird error messages. So typically, you can increase timeouts. There are a bunch of timeout settings, but there is an umbrella setting called Spark Network Timeout, which is 120 seconds default. But for like 10 terabyte, you should increase it to something like 600 seconds, or maybe more if you have even bigger data sets. Okay, so that was the configuration tuning information, and just to talk about the benchmark results. But before that, I want to show you like what hardware we used for the testing. And we at HPE, we have an infrastructure offering called EPA. We have a booth showing this. If you want more details, you can come there. But briefly, essentially in the here this architecture, we separated out the compute and storage so that you can scale the compute and storage independently. Essentially, the co-locating compute and storage was good in MapReduce days when it's all one workload. But as the workloads became diverse and like you have interactive and machine learning loads, which each of them require different server profiles, probably you want different server types. Like for machine learning, you want higher CPU cores, etc. But then people tended to have have different multiple clusters to solve these problems. But that introduces a problem of copying data between all these clusters. So to avoid that, essentially we separated out storage and compute. Now the storage is common HDFS layer. You can have hot, cold, and object. But more importantly, on the compute layer, you can have subclusters for Hive, MapReduce, and machine learning. Using yarn labels, essentially they're isolated. Now, and not on, for example, here I showed for DL360 for MapReduce, you can use some simple server like DL360. But if you're doing machine learning and deep learning, you can have higher end Apollo 6500 with GPUs, etc. Okay. So that's the architecture, but this is the real, for a single rack architecture on which the benchmark was done. Again, I'm not going to go all the details, but highlights like it's a building block based. So on the orange, you have the network blocks. There are 3 network switches. In the green, you have the management nodes where Ambari and your name node and resource manager and Spark history server are placed. And then below that, you have the purple, I guess, with the color, you have compute servers. Apollo 2000, it's a 2U box. It's a dense compute server. It's a 2U box with 4 nodes in each 2U box. And we use 3 of them in this reference architecture. So essentially, we have 12 worker nodes, 12 compute nodes. And then we have at the bottom, we have the storage for HDFS. There are 4 nodes. Each of them is 2U with, each of them has 28 large form factor drives. You can go up to like 10 terabyte drives, but we used 4 terabyte drives for this testing. Okay. Again, this gives a lot more details about that. You can go to the booth, and in fact, there is a virtual rack. You can have a touch and feel of that. But essentially, the key thing to note here is like the compute nodes have Xeon 16 cores, and we use about 512 gigabyte RAM. And then we use SSDs for intermediate storage. And then for this, I talked about the HDFS like this. Okay. This is a multi-rack. I'm not going to go into the details in the interest of time. So this is the benchmark results essentially. So as I said, the tricky part is figuring out cores per executor. So you need to, the bottom line is you need to experiment. That's what we did, because there is no guideline, simple guideline. So here on the y-axis, you can see total query time, and the x-axis, you see cores per executor. And I tried out from 1 to 45, 45 being the maximum allocated to yarn on per node in our configuration, 45 cores per executor. As you can see, the smaller number and the bigger number is not good, and there's an optimal number somewhere in the middle. And in this case, it happened to be 9, but your workload, you might get 10 or 8 or whatever. So just the keynote point is you need to experiment and figure that out. And the shuffle partitions, as I said, because again, that can be big performance bottleneck. So I tried with different, settings, like the default is 200, which is not good, as you can see from the experiments. And 540 is like the 45 per node, the number of cores, 45 per core, and we have 12 nodes, so 12 times 45 is 540, and I tried 1080 and 2160, which is multiples of 540. So we seem to be getting for 1080, we seem to be getting the best results. The compression, again, we took out the total disabled the compression, and obviously it's not good. And the snappy LZ4 and LZF are kind of give similar performance. LZ4 is the default in the middle, and that seems to be slightly better performance improvement. Okay, and now we evaluated, also the Spark 2 versus Spark 1.6. As Mark said, Spark 2 has a lot of improvements, particularly with SQL compatibility, because Spark 2 introduced, as Mark said, like a new native parser, and it has subquery support, so that it can run all the TPC-DS queries. Oops. Oh, okay. Sorry. Power. Did I do something? Oops. Sure.
I have another computer right here if you want.
Okay.
Well, there's no battery. It's dead. So is there
Typically, the SQL partition, that is the one which plays a big role in joins. So that is the key, and people have all kinds of problems with that. So the SparkSQL shuffle partitions, so that is the one which really plays a bigger role. Yeah, sure. Okay.
That is it, right?
Yeah.
Wait a second, is that turned on? Wait, I'll tell you. It's on?
When the number is high, that's a lot of I/O is very slow.
Probably that's because of the cloud. You are using it in cloud, right? It's different. This is all on-prem. You have a okay. Yeah. So it's for your own private cluster. So where it's the amount of cores you are using. So typically these tunings are for your on-prem. We haven't done cloud testing, so I need to think about why. There could be some reasons why they suggested. If you are reducing, that means typically the partitions will be too big, each of the partitions, because you have the reduce side, you are having only fewer partitions. That means you are pulling a lot more data into those partitions. So you might run into more issues, I would say. So, yeah.
So if I have, when I do a Spark submit,
Right.
I can set the parameters.
Yep.
Like
Yep.
executor load.
Exactly.
So if I have a job that comes in, I run the job with some settings. Now I have a second job that comes in.
Yeah.
Is there a way to, or what would be a good way to say, how do I look at that job? What can I look at and say for execution 1,
Yeah.
this data coming in,
Yeah.
let me set these parameters,
Yeah.
so it looks good.
Yeah.
Now 2 comes in,
Yeah.
I look at the what should I look at to say how do I set the parameters when running? So for each
Are you doing them concurrently or serially?
serially,
Serially, okay, that's easy part. Concurrently is hard, obviously, right? So the serially, any job, you have a Spark UI, right? Typically, it gives a lot more information than Hadoop, if you have seen Hadoop. So the Spark GUI has all kinds of the stages and the tasks and the partitions, and you can see the graph. So you can see, and the memory, even the storage, how much storage it's taking. So you can click through all those things. It gives a lot of information. That is your best bet for tuning, right?
no, like I'm saying,
Yeah.
no, that's right.
Yeah.
I'm saying if a new if I don't know what's going to come,
Right.
but what would be a good way to say,
You got it?
let me look at these 10 heuristics or parameters,
Yeah.
and based on this is what I think I should set for my job.
So again, typically you don't want too many. One of the key things to look for is how much memory, obviously, because are you running into spills, right, onto disk, which will slow down, right? And then because again Spark can make use of cores very efficiently, how many executor cores per executor, those are the key ones, and the per joins and all SparkSQL shuffle partitions, yeah. So those are the key ones, I would say, right? And then beyond that, you might tune this and all those things like serialization, and then those things you want to try, and unless you have to experiment, I guess there is no.
Let's go through the results.
Yeah, okay. So just finish off quickly on this, and then I'll take the questions, right? So, okay, let's quickly finish. Yeah, also this one.
I think you did that one.
Yeah, so, and then just the robustness part, they said, Spark 1.6 could not even start all the queries because it didn't have support for subquery. And then even for those which started, it could not finish with 10 terabyte. With 1 terabyte, the query is finished, but with 10 terabyte, it could not. Whereas Spark 2 or 3 both, they can.
About 4 minutes, 3 minutes.
Yeah, I'm almost done.
Okay.
So this is the total overall improvement, for this queries. Essentially we got about 2.3 times, improvement in Spark 2 versus Spark 1.6. And these are some more details about the queries, as you can see, individual queries, how they perform. Obviously, some of the queries benefit a lot. I'm assuming that they did some I didn't drill into all the queries, but sometimes that's the way SQL I've worked on. MPP SQL, so you tune something and then dramatically goes down. But overall, the key thing is every query gets benefit using Spark 2. Okay, if you can see the orange, everything is down. And this is another experiment we have done for performance, see the scaling aspect of Spark 2. So essentially, again, this is key for our EPA, Elastic Platform Architecture, because the promise here is by adding more nodes, you are able to improve your performance. So I did experiment with 4, 6, 8, and 10. So as you can see, by adding more nodes, the total query time comes down almost linearly. The solid graph is actual points, and the trend the dashed line is the trend line. I think that's the last slide I have. Okay, Mark.
Oh, yeah.
Finish it off.
So here's some links for you guys to check out more information. Obviously, there's you'll be at the booth tomorrow.
Yeah, I'm at the HPE booth. Number is P4 or something.
But let's open up for questions in the last couple minutes. We have 2 minutes. We have 2 minutes left. Sorry about the delay.
Yeah, I think he has a question.
And if you could use the mic, it'll help.
Oh yeah, sorry, you didn't mention that. Maybe
if you don't mind.
You should have repeated the question.
If not, don't worry about it.
Okay. I'll repeat. Okay.
Don't worry about it.
Yeah. So one of your slides that you showed cores per executors.
Right.
The graph went up again, for 40 cores or something.
Right.
Was the memory capped, executor memory capped for 5 executors and 40?
Yeah, the total memory is capped because we have only so much memory, right?
So is that because of 40 threads running together, hitting the JVM heap, hitting the memory?
That's a good question. Actually, potentially it could affect, but I didn't see a memory pressure. In general, 10 terabyte, and we had a lot of memory. Exactly, it's most likely because of the too many threads and shuffles involved, creating all these intermediate files. So more partitions means more executor means you'll have more core files, and you have to do more I/O.
Because on the contrary side, can give performance benefits also, because a single chunk of data is processing is done in the single executor, and there's no shuffle. Also, sometimes for some queries that can be beneficial because.
Oh yeah, if you don't have shuffle, this is for shuffles. That one particular.
Let's take one more question.
Yeah, sure. 256 or 512 base, yeah. Yeah, it won't help in this case. This was clearly for bigger files. In that case, default 128 MB is good bet, I guess. You won't go up beyond that. I know.
So we're getting thrown off. So thank you
Yeah, the
very
default
very
is
much.
good enough in
Let us
general.
know if you have any questions.
Thank you.
Okay.